Welcome back, everyone. This is our second part of our linear regression analysis lecture. In order to get this into a somewhat compact time frame, I'm going to have to kind of jump and hit the high notes. So please do your best to follow along, bear with me, so that we can get this done in an online format. You may recall, make sure you've reviewed the linear regression analysis part 1, so you have a general understanding of when we use linear regression and how it's just a further expansion of the test that we've been doing under the general linear model. So for this one, we're going to start off by taking a look at the SPSS output for linear regression. It's going to look a little intimidating at first, but once again, bear with me. I think you'll get it, and once we sort of compartmentalize things, where we need to find something, what we need to find, you're going to notice it looks a lot like the types of information that we've been pulling from other analyses. Then we're going to dive into looking at what is known as the linear regression model or the equation. The reason for this is because linear regression, not only are we looking for associations between variables, but we're also trying to develop predictive models. So we want to see, by knowing certain factors that you might have, what's your likely value on some outcome. And so that's what we're going to be seeing with this. We're then going to dive into both bivariate regression and multivariate regression. Bivariate regression is when you only have one independent variable. Multivariate is when you have more than one. So we'll see how those slightly change what we're looking at, and we'll go from there. Finally, for this slide, the reading that corresponds to this would be Chapter 9, Module 20 of the 4th edition of your textbook. All right, let's go ahead and get started and dive into the next slide. So what these next two slides are going to look at is what is the SPSS output look for when we're doing linear regression. So the example that I have here is I'm trying to figure out or predict an outcome. And that outcome that I'm trying to predict is how many dollars a drug dealer is going to earn each month from drug dealing. So if you look at the top of this output, you'll notice it says DV, dependent variable, right, our outcome. And I'm trying to predict the dollars earned from drug dealing per month. Then in the first model, what we're going to call model 1 in just a few moments, I am only going to introduce my first independent variable. And my independent variable for model 1 is years of experience in drug dealing. And you'll notice at the top of the slide where it says IV1 equals years of experience in drug dealing, I don't have to have any coding. Why? Because it is a continuous variable, right? So all I need to know is the number of years, and I can enter that directly into my model. Then in model 2, we're going to add in a second variable. And that second variable is going to be the type of drug sold by the dealer. And in this case, you'll notice the type of drug sold is in fact a categorical independent variable. And it has 3 levels or 3 categories to it: marijuana, cocaine, and methamphetamine. And so what I need to do, if you recall from our last lecture, is I need to dummy code that variable into 2 dummy variables. So if you look down also at the top where you see dummy variable 1 and dummy variable 2, you'll notice that I have a dummy variable for cocaine, where everyone who is a cocaine dealer gets a value of 1. All other types of dealers get a value of 0. And then I have dummy variable 2, which is methamphetamine. So people who are a meth dealer get a 1, everyone else gets a 0. The one group that is left out is my marijuana dealers. So you may also recall from our last lecture that that means that marijuana becomes my reference group. And we'll see that when we go into a little more detail. Then the first major box we see says variables entered / removed. So this tells us, or tells the reader, what independent variables were entered at each stage. So in model 1, you'll notice I just have years of experience. Then in model 2, we add in those 2 dummy variables that capture the type of drug sold. We enter in the cocaine variable as well as the methamphetamine. And the spirit of this with linear regression is that it allows us to start to add in more predictors, more factors that may tell us about some sort of outcome. And that's sort of the cool thing with statistics and why linear regression is such a useful and amazing tool for us. All right, then you see the footnotes for that variables entered and removed. It says all requested variables are entered. That's just how it was entered through SPSS. I said enter it and don't take it out. That's all that means. Then it has our dependent variable where it says under footnote B, dep var or var. That's our dependent variable, which is dollars earned from drug dealing per month. So it's letting us know that. Now let's take a look at the very bottom table that we see on this particular slide. The bottom table says model summary. Okay, we will see this as we go through some of the steps of interpreting and finding the important information on the following slides. But overall, the model summary tells us the strength of predictability that our particular regression model has. And we're going to be paying a lot of attention in a few slides to mainly the R-square column and the adjusted R-square column. That gives us a lot of information about just how strong our overall model is. So we'll see that, so keep that in mind. Let's go ahead and move on to the next slide. So in this slide, this is a second sort of part of the SPSS output for linear regression. The top table here is an ANOVA table, and you may go, oh, I remember an ANOVA table. Yeah, this is the cool thing about regression. It has built into it, it's pretty much things we've learned already this semester. We're going to see R, correlation statistics. We're going to see F, ANOVA statistics. We're going to see T statistics, things that we've already talked about, and we're building towards a bigger, better statistical model. So some of this stuff hopefully you'll recognize. All right, so back to the ANOVA box. The ANOVA box may look rather familiar, especially let's just focus only on model 1. And you'll notice if you look at for all of these tables, if you look over to the far left-hand side, you'll always see it says model. And then we have 1 and 2. And that's going to be important as we go forward in this lecture because model 1 is the model where we only had years of experience. And you'll see that also in the footnote A for the ANOVA table where it says predictors, it says a constant, we'll come back to that, and years of experience. And then in model 2, it talks about we have added more material into it or more factors into it. So let's just look back to the ANOVA model 1. You'll notice that it looks very similar to what we saw when we saw a standard one-way ANOVA output where we have a sum of squares column, a degrees of freedom column, a mean square, an F, and then a p-value for the F. It's the exact same logic, except over there in the model 1 box on the left-hand side where it says regression, regression is just substituted in for what we were calling between groups when we did ANOVA. Residual is just substituted in for what we were calling within groups. So the logic is going to be the same. So we're going to talk about how we use that ANOVA box to interpret our findings in the next couple slides. Finally, we have the coefficients box. The coefficients box is that box at the bottom of this slide. Here is where we start to get a deeper look into how individual factors or individual independent variables influence our particular outcome. And so you'll notice once again, when we look at just the model 1 row, when we look at the model 1 row, you'll notice it says there in parentheses, it says constant. This is just going to be an intercept, and we'll see that when we talk about how we build the model in the next slide or two. And then it has the one independent variable that is introduced in that model, which is years of experience. And then as we read from left to right, we'll talk about unstandardized coefficients. We'll talk about T, and T is just like we've seen before. We'll see SIGs, that's a p-value, and that's going to be sort of our main focus. There's other things in this box like standardized coefficients, the different types of correlations, the collinearity statistics. For the sake of this course, don't worry about those. In this coefficients box, we want to focus on the capital B column under unstandardized coefficients, and also we want to focus on the T column and the SIG for the T statistic. Those are ones that we'll talk about a little bit later. Finally, before we move on, you'll notice model 2 in that same coefficients box. We've added not just years of experience, but we've also added in those 2 dummy variables in order that capture the type of drug sold. So we see cocaine and methamphetamine. And this is like I don't know, I'm sounding like a nerd, but this is where it gets fun because we start adding in more information to give us a better idea about to predict our outcome. And I don't know about you, I mean, I'm not trying to predict how much people are going to earn from drug dealing, but hey, if that's your thing, that's your thing. Okay, let's move on to the next one. So before we can start breaking down the output, we have to kind of understand a little bit about what the heck is linear regression. And when people talk about a linear regression model or a linear regression equation, that's the purpose of this slide. So earlier this semester, we talked about Pearson's R. Remember that correlation coefficient? And we talked about how it was, in order to predict the association between 2 variables, it was trying to draw a linear line, or I guess that's redundant. It was trying to draw a line in order to predict the association between 2 variables. Linear regression is just an expansion of what we learned about with Pearson's R. So if we were in class and I had access to the whiteboard, I'd be showing you fancy scatter plots and things like that with a regression line. But for right now, let's just keep that idea. So what you see here, let's read the red bolded material at the top of this. It says the linear regression model / equation. And then in parentheses, this, even though you may not recognize the use of the various letters, this is simply the equation for a straight line. And so in this case, y hat, and y hat is usually done as a symbol with a y with a little like inverted v over the top of it. For the sake to get us through this, I'm just going to call it y hat, and we'll come back to what it is. Equals b sub 0 plus b sub 1 times x sub 1. Okay, so what are those various components? Well, first of all, that y hat, that's the predicted value of our dependent variable. So for our example, we're going to be talking about, we're trying to predict how much money is a drug dealer going to make each month. Well, if that's our outcome, we're trying to predict it. Now, once again, we're working with sample data, so we're never going to be 100% perfect. There's always going to be error. That's why we're referring to it as the predicted value of the dependent variable. So that's that y hat in this mathematical equation. Then we have b sub 0. B sub 0 is what you may recall from your old algebra classes as the intercept. And the intercept in SPSS and with linear regression, we find the value of that on the output by looking for the constant value. And you'll notice the arrow there leads down to the constant, and then we'll be talking more in a little bit about, we're going to focus on that capital B, the unstandardized coefficients. And so we see for the B sub 0, that 158.783, that's going to be important to us a little bit later. We also, another important part that we find from the output is what is known as the B1. B1 is a regression coefficient. It's an unstandardized regression coefficient. For those of you thinking about back to your algebra classes, it's your slope coefficient. It's rise over run. So that's all this is. And so that unstandardized regression coefficient, B1, is the slope coefficient for our first independent variable. In this model, we only have one independent variable, so we don't have to worry about it too much. So that is years of experience. So X1 is our years of experience. Finally, we have, you'll notice there in black, I say X1 equals value of the independent variable 1. All right, so when we're building an equation or a regression model, we want to use it to make predictions. I want to know what kind of drug do you deal with, how much years of experience you have in order to predict how much money you're going to make from drug dealing. So I can enter the value for you. If you're somebody who has 1 year of experience, I enter that into the model. If you have 2 years, 3 years, 4 years, whatever it is, I just enter that value into the model, and then I can make a prediction for that thing we called y hat, the predicted value of the dependent variable. So for us right now, this is going to be sort of our background that we're going to work with as we walk through breaking down and understanding the important parts of the SPSS output. So let's go ahead and move on to the next slide. So in model 1 of the output that we saw on previous screens, this is what is known as a bivariate regression. So bivariate regression just means that we only have 2 variables involved. We have 1 independent variable, we have 1 dependent variable. And in order to make sure that a regression, linear regression, can handle it, we want to double check what are the requirements of the independent and dependent variables for linear regression. So you'll notice here in red, I say that we can only we have 1 independent variable in bivariate regression, and it can be either continuous or categorical. For our current example, our independent variable is continuous. It's years of experience in drug dealing, so it's at that interval or ratio level of measurement. And also, we can only have 1 dependent variable, and it has to be continuous. And if you look at what our DV is, that's circled in red there, dollars earned from drug dealing per month, that is at that interval or ratio level of measurement. So in this bivariate regression example, both our independent as well as our dependent variable are continuous. When we get to model 2, we'll add in a categorical variable with those dummy variables that we talked about a little bit earlier. Let's go ahead and move on to the next slide. So the one thing that I'm going to try my best for you guys to understand for the sake of linear regression for this semester are the 3 components that we want to be able to take away from the SPSS output. So there are 3 things we need to be able to recognize. 1, we need to talk about whether or not what we call the overall model. Is the overall model statistically significant? And I'll come back to that. 2, we're going to talk about if we have more than 1 independent variable, are the individual independent variables statistically significant? And then finally, we're going to talk about how we can use linear regression to make predictions. And that's kind of like I've said, I think I've stressed it enough. That's the cool part that I like. So for this bivariate regression, we're only focusing from the output we saw before on model 1. So in order to figure out the overall model, what the hell do I mean by the overall model? The overall model is if we take all of the predictors, all of the independent variables in our linear regression, do they as a team or as a set, do they together have a significant association with the outcome? In this case, the outcome is money made from drug dealing. So that's what when I talk about the overall model does, when we take the entire set of independent variables when taken together, are they significantly associated with your outcome, your dependent variable? Now note, and we'll keep this simple, this is a bivariate model. So there's only 1 guy on this team. And I could do some sort of basketball analogy about Michael Jordan or Kobe Bryant, but in this case, we'll keep it somewhat short. There's only 1, in a bivariate model, there's only 1 independent variable, so the quote-unquote set or the quote-unquote team is simply that 1 independent variable. When we move on to model 2 and we add in more predictors, you'll get a better idea of what I mean by the set or the team. Okay, so what do we take away? So if somebody asks you, hey, is the overall model statistically significant? You look to that ANOVA table on your SPSS output. And what do you take away from it? You take away the F statistic, you take away the p-value from that F statistic, and you also make sure to report both the two relevant degrees of freedom. So a lot of this should be somewhat of a flashback of what we did with the ANOVA F test. It's just the only difference is the between groups is referred to as a regression, and the within groups is referred to as residual. So when you look at sort of my summary, below where I say, or near the arrow where I say ANOVA summary table F test, you'll see I have F with degrees of freedom 1 and 38 equals 6.890, just taken from the output, and P equals 0.012. So we should probably also be familiar with the idea that because my p-value is less than 0.05, right? 0.012 is less than 0.05. I can say, yes, my overall model is statistically significant. And you can also even use the term like that we talked about earlier, the rejecting the null hypothesis. But now that we moved on regression, we're just going to use the word significant or not significant as the more common way that we interpret this stuff. So because the p-value for my F statistic is less than 0.05, I can say, yes, the overall model is statistically significant. Now, a follow-up question somebody may ask you is, well, okay, so it's significant, but just how strong is your model? What's the strength of your model? That's where we can look to another piece to give us a little bit more information about the overall model. So let's go ahead and move on to the next slide. So in order to figure out the overall strength of the overall model, not just is it significant or not significant, but what is the strength, we often look to a coefficient of determination. And you may go, oh, I remember that from somewhere. Yes. Do you remember the Pearson's R from beginning or earlier in the semester? This is just an expansion of that same statistic. And it tells us the percentage of variation in the dependent variable that can be explained by the independent variable. So in this particular example, it's a bivariate regression, so we only have one independent variable, one dependent variable, which adds to 2. So it's telling us the percentage of variation in money earned from dealing drugs that can be explained by the independent variable, which is years of experience. So where do we find that? Well, they give you, and you can see circled in red in the model summary box, for model 1, there is a capital R of 0.392. That capital R is technically known as multiple R. And it's really just behaves very much like the normal lowercase Pearson's R. So that R of 0.392, okay, we have a positive association, good. But we can square R, to see that 0.153, to get an answer about the percentage of variation in the dependent variable that can be explained by the independent variable. And we had another PowerPoint slide earlier this semester where I brought up the coefficient of determination when we talked about the Pearson correlation coefficient. So you can always look back to that if that will help you. The one other thing on this is you'll notice I also have listed here the adjusted R squared. Well, why do I have R squared and adjusted R squared? Similar to when we talked about biased versus unbiased standard deviation formulas a month or so back, we also in statistics will produce 2 versions of R squared. R squared is very accurate for that particular sample that you're working with. Adjusted R squared, however, is going to adjust for the fact that you're working with sample data, and it tends to bring the value down a little bit, which makes it a more, I guess, honest or valid assessment when you're using that sample data to try to make estimates about the larger population. So how would I interpret either R squared or adjusted R squared? Well, R squared, if it's 0.153, it tells me that 15.3% of the variation in dollars earned from drug dealing can be explained by years of experience. The adjusted R squared is interpreted in the same way. It is just a more accurate assessment when you're trying to use this statistic for inferences to the larger population. So adjusted R squared is 0.131. So that would mean that 13.1% of the variation in money earned from drug dealing can be explained by years of experience. Okay, so that's the technical interpretation. But in the reality of research, what you're trying to do is you want to get the biggest R squared or biggest adjusted R squared you can get. So hopefully we'll take a look. Think about this when you go to Model 2. Model 2, which you can see right below it, you'll notice that both R squared and adjusted R squared get bigger. So we're explaining more of the variability in money earned from drug dealing. Why are we explaining more of the variability? We are because we've introduced another factor into the model. We're not just taking into account how much does years of experience influence money earned, but we're also taking into account the type of drug that the particular dealer is selling when we get to Model 2. So that's why we see those values go up. Typically, when it comes to which one should I report, do I report R squared? Do I report adjusted R squared? What do I do? Adjusted R squared is the go-to because it tends to adjust for discrepancies or errors or over predictions that R squared handles. And if you happen to introduce a variable that is not a good predictor of the outcome, adjusted R squared can actually go down if you put like a bad predictor in. So my go-to, when somebody asks about the significance of the overall model and coefficient of determination, I go with adjusted R squared. All right, now that we've talked about the significance of the overall model, which to quickly review was look at the F statistic and its p-value from the ANOVA box to tell you whether or not the set of independent variables are a significant predictor. And then if somebody says, well, how strong is your model? We look at the coefficient of determination, R squared or adjusted R squared, to get an idea about percentage of variation that we're explaining. Now, let's imagine if we want to examine the influence of specific independent variables. So let's move on to the next slide. So the second part of the three components that can be taken from the SPSS output for us is the idea of how do we test the significance of individual predictors. So in order to find that information, we look to the coefficients box. So the coefficients box is usually the last box that you'll see at the bottom of your SPSS output. And we're looking at actually its individual t-tests for each of the predictors. So for us, when we look at Model 1, you'll notice Model 1 only has one independent variable, years of experience. So when we look over to the t column, we see only a t for years of experience as well as its associated p-value. Above it, we have the constant. And that constant, you may recall, is the intercept. And we'll see where that comes into play in a couple slides. So let's not focus on that. So if I say what is, for the specific individual independent variable, years of experience, is it significantly associated with money earned from drug dealing? You would look to that coefficients box, the row that says years of experience. You find the t, which is 2.625, as well as its associated p-value, which is just labeled as a sig that we've seen before. And you'll notice the sig happens to be 0.012. That's less than 0.05, which has always been our cutoff point. So we can say, yes, years of experience is significantly associated with money earned from drug dealing. So because we only have one independent variable, that's all we can focus on. And you'll notice that it was actually the same outcome that we had with the F. In fact, I think the p-value is exactly the same, 0.012, because our overall model, quote unquote, is the same as all of our individual predictors. So that's what the idea of the bivariate. All right, so let's go ahead and move on to now what I think is the most interesting part of it is how do we make predictions? Now that we've done one sample run, collected data, let's say we have a new drug dealer come up to us and he's going, how much money am I going to make, right? I mean, so maybe it's like a stockbroker, maybe it's a gambler, but in this case, we're talking about a drug dealer. Okay, let's move on to the next slide. All right, so when looking at this, one of the things that's going to go into that is what is the influence of that that one independent variable. So we talked about it being significant on the prior slide where we looked at the t value and looked at the p value for that particular t value. But there's another important piece that is given to us in that coefficients box, and that is the actual unstandardized regression coefficient. And so what you see circled with an arrow pointing to it down here is the unstandardized regression coefficient for years of experience is 39.540. So you can find it in the unstandardized coefficients column under the capital B and in the row for that particular independent variable. And what does this tell us? Well, this is the slope coefficient. So once again, taking you back to your days in algebra, this is the change in y for a 1 unit increase in x, rise over run. How does my dependent variable change for a 1 unit increase in my independent variable? So that b, which in our equation that we'll see in the next couple slides, b sub 1, my slope coefficient is 39.540. What does that mean? That means for each additional year of experience in dealing drugs, the amount earned from drug dealing each month will increase by $39.54. And so you'll notice it's a positive value, so that's why it's an increase. If it had been negative, that would be a decrease, right? So the numbers just go as numbers do, but it's change in y for a 1 unit increase in x for each additional year of experience, which is my independent variable, the amount earned from drug dealing. My dependent variable will increase by $39.54. So that gives us a little bit more of a story about how strongly a particular independent variable can influence the outcome. Let's move on to step 3 for the 3 components that we want to make sure we take away from our. All right, so step 3, as I've been alluding to throughout this entire thing, is what my favorite is, developing predictions, right? So we live in a world, especially in criminal justice, if we have to release people from prison, if we have to sentence somebody, we're always looking for prediction instruments to try to figure out what's the outcome going to be. That's the core of linear regression. And even for people who are really into gambling, they can do some pretty darn good gambling if you develop the right linear regression model. It's all about figuring out what factors are going to make me successful, or with offenders, what factors are likely to make somebody more or less likely to recidivate. Whatever your outcome is, a regression model can allow you to add in multiple factors, and by reviewing the significance of the model, reviewing the coefficient of determination, the r squared and the adjusted r squared, and looking at the significance of specific independent variables, you can build a perfect model that can get you the best predictive ability that's out there. And that's really what we're trying to do with research, is predict, why does crime occur in one place but not another? Why does one person make more money than another, etc. Okay? So how do we do this developing of predictions? Well, what we need to go back to is our basic linear regression model, or our linear regression equation, which with a bivariate regression is that simple. It is the equation for a straight line, right? So it's that y hat equals b sub 0 plus b1 times x1. And let's remember what each one of those things mean. Y hat is the predicted value of money earned. It's the predicted value of our dependent variable. What is b sub 0? B sub 0 is the x-intercept if we were to actually plot this on a graph. And where do we find b sub 0 on our SPSS output? We find it in the constant row under the unstandardized coefficient. Then we have B sub 1. B sub 1, we've seen before. This is our regression coefficient or slope coefficient for our first independent variable. So our first independent variable happens to be years of experience. And you'll see that it has a B1 value pointed to with the yellow, or excuse me, with the blue arrow of 39.540. And then finally in this model, we have X1. What's X1? X1 is the value of years of experience. So you could enter in any particular value you want, depending upon the person you're working with. So let's look at our example. Let's say that Joe comes across and he has 3 years experience dealing drugs. So how many years of experience does he have? He has 3. So we're going to enter that into the model. So how much do we predict he will make per month? Well, if we enter his values into the model, the things that will stay the same here are the constant, B sub 0, and B1, the regression coefficient for years of experience. So we see if we're trying to predict his money earned, we have that 158.783 plus 39.540 times 3. 3 is what we introduced for his years of experience. If we solve that out, we can predict that Joe will earn $277.40 per month based upon this particular regression model. And that's in a nutshell how regression works. Let's go ahead and take a glimpse, and also I encourage you to practice along. I'm not going to have the cutouts and the pictures of the SPSS output. As we move into multivariate regression, I'll just give you some talking points, but I want you to try to either look at it on a different slide, print it out, whatever it is, and then you can kind of walk through to see that we're going to see the same ideas with just a couple little tweaks because we're now introducing more than one independent variable. So let's go ahead and move to the next slide. All right, so when we move on to multivariate regression just means we're adding more than one independent variable. So we started off with a single independent variable, which was years of experience. Then we wanted to add in type of drug sold. However, since type of drug sold was a categorical independent variable, we needed to dummy code it into k-1 dummy variables. So what the model actually looks like, if you go back and look at the output for model 2, it looks like we have 3 independent variables. Why? Because we have one, which was years of experience, which was continuous, no problem, leave it in there. And then we had those 2 dummy variables that help us to capture the idea of type of drug sold. So let's go through the key differences from the bivariate example. So we've added a second independent variable. Because it is categorical, we dummy coded it with you see that, and we use marijuana as a reference category. What does this do to the linear regression equation or the linear regression model? Well, if you look at point 2 on this slide, what this does is it just starts to add in more slope coefficients, more regression coefficients. So the linear regression equation adds in the additional independent variables, and you can see that illustrated there. And we'll see that when we get to the predictions in a few slides. Also, the ANOVA test itself really does differ from the quote-unquote t-test that we saw in the coefficients box, because the ANOVA test is really truly testing the overall model, meaning as a team, how well does that team predict the outcome, or in this case, money made from drug dealing. And then our regression coefficients, I'm not going to stress this too much in this class, but because we have more than one independent variable, we now call them partial regression coefficients as opposed to just regression coefficients. Why is that? Well, it's because the model is distilling the sort of the unique influence of each independent variable on a dependent variable after controlling or adjusting for the other independent variables in the model. So the cool thing, another cool thing about linear regression is that by looking at these partial regression coefficients, you can figure out, ooh, that particular independent variable is a stronger predictor than another independent variable. So you can figure out, just like you would do on a basketball team or any other sport, you can figure out who is the all-star, who is the MVP of this team, and amongst the various independent variables. And you'll notice that the interpretation of these regression coefficients slightly change. We just add in that phrase, controlling or adjusting for other variables in the model. All right, so let's go ahead and talk through the steps about the three things we want to pull from the SPSS output as they would apply to a multivariate regression. Let's move to the next slide. So testing the significance of the overall model, which is step one, we would start by looking at the ANOVA table, just like we had done with a bivariate regression. And even though I don't have a picture of the output on this slide, you can refer back to it or print it out, whatever works. But see if you're able to find the information that I have there, where I have an F statistic with degrees of freedom of 3 and 36. The F statistic value is 5.253, and the p-value for the F statistic is 0.004. So because the p-value is less than 0.05, I can conclude that the team, the overall set of independent variables, are significantly associated with the dependent variable money earned from drug dealing. I can also, if somebody says, well, how strong is it? I can look at the coefficient of determination, which is either the R squared or the adjusted R squared. And you'll notice, as I mentioned before, you'll see that these are higher values than the values we saw for the bivariate regression in Model 1. Why? Well, because apparently it looks like the type of drug you sell does also contribute to the money you earn. So that's why we're getting better at our explanatory ability. And that's kind of the goal when doing regression, is we want to explain the world, right? So that's where this kind of goes in. Those R squareds and adjusted R squareds are, if those start to go up, we get excited. Let's just put it that way. That's what tells us we've really found something interesting. We found something significant. We have the ability to explain associations and make predictions. All right. And then I did add on this slide at the bottom that the adjusted R squared is often better to report. And this is similar to what I mentioned on a previous slide, but it's just sort of having it there so you can refer back to it later. Let's move on to the next slide. So with this one, now we're looking at the significance of individual predictors. And you'll notice because we have moved on to multivariate regression, it's kind of cool. We have multiple independent variables. So we can say, are all of them significant or only a couple of them, right? Or maybe none of them. So by looking at that coefficients box and then the t-test for each one of the independent variables, we can see which independent variables are contributing to the overall association and explanation or prediction for the outcome variable, the dependent variable. So years of experience, you'll notice that it has a t of 2.649, a p-value of 0.012. So it is, because it's less than 0.05, that is in fact a significant association. You look at type of drug sold. Well, in order to capture that information, as you may recall, we had to report the dummy variable values. So we had to create two dummy variables, cocaine and methamphetamine. And then we want to see which one of them has a significant association with how much you make. And you'll notice that for cocaine, it has a p-value of less than 0.05. It has p equals 0.015. So cocaine is a significant predictor. However, methamphetamine does not appear to have a significant impact on the amount of money earned. How do we know that? Because we look at the p-value for methamphetamine and we see that it's a 0.874. So interpreting these partial regression coefficients that would come with it, as I said, we can also get those those unstandardized coefficients, the capital B column, and each one of them has a value for that. So it's still the idea of change in the dependent variable for a 1 unit increase in the independent variable. But then we add in this little statement, after controlling for the other independent variables in the model. That's just sort of like, canned language that you find in statistics. So for years of experience, you'll see it changed a little bit from model 1. Why? Because it's been distilled, it's been clarified, it's been made more pure. By adding in another variable, we get a better idea of just its unique experience or its unique influence. So you see that the B1 equals a 38.988. So we could interpret that by saying for each additional year of experience, the amount earned from drug dealing each month increases by $38.99 after controlling for type of drug sold, which is the other independent variable in the model. And then one of the things that I'm not going to go into great detail here, but I'll just sort of mention it. When we are interpreting our dummy variables, the true interpretation is a comparison between that particular category of the independent variable versus the reference category. And I know that gets a little bit crazy and I don't want to throw too much at you right now. I'm going to care more about knowing whether or not specific variables are significant, which was sort of the t-test and the p-values for them. But just to give you a glimpse into it, if we look at the bottom of this slide where I say type of drug sold, you'll see I make that note about what I spoke to, which because we are working with dummy variables in the interpretations, the interpretations will be comparisons made with a reference category. So since cocaine, which is a significant dummy variable, because it had a p less than 0.05, because it had a coefficient of 248.186, I could interpret that as saying cocaine dealers tend to earn approximately $248.19 more per month than marijuana dealers after controlling for years of experience. So the 248.19 was from the actual B2 coefficient being positive. And then the comparison was to the reference group, which is the one that we left out, which was marijuana. All right, let's go ahead and move ahead. And then finally, when we look at the developing predictions for individuals, this is where you can imagine, and just to give you a quick glimpse, this right now, this multivariate regression has a total of three B's, right? 3 independent variables. You have your constant B0, which doesn't really count, and then you have B1, B2, B3. As you're working with larger samples or trying to put in more factors, you can imagine a regression model that could have 5, 10, 15 predictors. I know when I was working on my dissertation for my PhD, and I was doing a model that focused on predicting regression outcomes, or predicting recidivism outcomes, I want to say that my final model had something like 18 or 19 total B's or total like predictors in it. So you can imagine it gets really large, but you can break each one down just like we're doing with these ones in a very simple, like focus on it one at a time manner. So you'll see that under the developing predictions for individuals, it says y hat equals, and you'll see the B0 plus B1 plus B2 plus B3. If we had a fourth independent variable, we would just add it in there. It'd be B plus B4X4. So you just keep going in a very linear fashion in that sense. And then what I've done for the predicted money earned was I went to that unstandardized coefficient column, the capital B's, and you just insert the values as they correspond to the constant of 69.803, and then for each one of your particular predictors that you have in the model. Then the X's just become the values for those. So we look at our example of Pete. Pete has 2 years of experience selling cocaine. So I've given you all the information you need in there to fill out this particular mathematical equation and find out what is Pete's predicted earnings. So how much would we predict him? How much would we predict he makes each month? So you'll notice I keep those B values, the coefficients in there, and then next to the 38.988, because he has 2 years of experience, and that's the one that corresponded to years of experience, I multiply it by 2. I move on to the 248.186. That's the cocaine variable, right? And remember, the cocaine dummy variable was, if you're a cocaine dealer, you get a value of 1. Anyone else gets a value of 0. Well, he happens to sell cocaine, so he gets a value of 1 there. We move on to the other one, meth. And the meth, he was not a meth dealer, so he doesn't get credit for that. So he gets a 0, so that'll cancel that out of the equation. So by doing that and then just doing the basic math of solving it out, we would predict that Pete will earn $395.97 per month. So what's the takeaway? Well, that's a somewhat short, although it took me 50 plus minutes to talk about and introduce linear regression. But it also shows you that if this data is actually true, that dealing cocaine, even if you've done it for 2 years, may not be a good way to survive in Southern California by making less than $400 a month. So take care, and we will move on from there.